Hey everyone, welcome to This Explainer. I'm your host, TheInfoEngineer, and today we're going to completely dissect a fundamental engineering mystery. We rely so heavily on complex automated systems to fly our planes, navigate our massive ships, and manage our day-to-day risks. Yet it is honestly mind-boggling to think that a $100 million machine can sometimes be completely outsmarted by a 20-cent piece of tape or just a single dead bird. Today, we're unpacking the anatomy of an automation failure to really understand the crucial intersection of systems, sensors, and physical truth. All right, let's dive right into this. I want to hook you right away with a question that literally keeps engineers like we awake at night. Do sensors actually lie? Seriously, how is it possible that multi-million-dollar flight control systems or advanced maritime navigation networks can be brought down by a single damaged weather vane, a patch of ice, or a spoofed digital signal? It almost feels like the machines are turning on us, right? But the reality is actually far more structural. Here's the bottom line right up front. Sensors don't lie. Systems fail. To maintain our professional standing as engineers and analysts, we have to recognize that these massive, headline-making disasters are rarely just simple hardware failures caused by a bad sensor. Instead, they're profound failures of system architecture and logic design. The hardware did exactly what it was supposed to do, but the system couldn't interpret the context. Section 1. The lying sensor myth. We have this habit of anthropomorphizing our tech. We like to think a sensor is maliciously lying to the computer. But sensors are really just honest, albeit pretty dumb reporters of their immediate physical environment. And this brilliantly illustrates the concept of erroneous data injection. According to the FAA's review of the Boeing 737 MAX, there's a specific failure scenario where a sensor's electrical circuit is perfectly fine, so the central computer flags the incoming data as valid. But what if an angle of attack vane on the outside of the aircraft is physically bent by a bird strike? Well, the sensor honestly reports the bend. It's functioning perfectly, but it's feeding valid erroneous data into the system. The sensor isn't malicious, it just has zero context. Section 2. Redundancy and the voting concept. So, you might be wondering, if individual sensors can be physically compromised so easily, how does modern engineering prevent a single broken sensor from causing a total catastrophe? Let's look at the hardware defense layer. The answer is redundancy, specifically a concept known as triple modular redundancy, or TMR. This is absolutely one of the most important technical takeaways in automated architecture. Imagine you have 3 sensors measuring the pitch of an aircraft. If sensor A says we're pitching up and sensor B says we're pitching up, but sensor C says we're pitching down, this system takes a vote. Because the majority agree, the system knows for sure that sensor C is failing and simply ignores it. Take a look at this engineering blueprint. It's derived from a Brazilian Congress of Mechanical Engineering paper on redundant sensors, and it outlines a 4-signal voting algorithm. Notice that block labeled miscompare. Modern flight computers are constantly comparing incoming signals. If one signal suddenly diverges from the voted average, say an instantaneous miscompare, the algorithm rapidly isolates that flagged fault. This mathematical voting process is exactly how modern aircraft manage to stay safely in the sky despite individual sensor failures. It's a really elegant solution. But hey, we don't just vote, we also merge. And that brings us to sensor fusion. As outlined in our sources, sensor fusion is the process of combining data from totally disparate sources, like accelerometers, GPS, and radar, so the resulting information has way less uncertainty. The system calculates a single, highly reliable middle value, filtering out the noise and the outliers to pass on to the flight control laws or the navigation displays. Section 3. Visualizing systemic bias. But, and this is a massive but, here is where the whole architecture breaks down. What happens when an entire family of redundant sensors is compromised at the exact same time? Voting only works if the sensors are truly independent. We call these vulnerabilities common mode environmental blinds. Environmental factors can create a systemic bias that blinds redundant sensors simultaneously. Think about it. If all 3 sensors are covered in the exact same sheet of ice or subjected to the exact same maritime GPS spoofing interference, they're all going to agree on the exact same incorrect data. An electronic fog settles in. The voting algorithm thinks everything's completely fine because all the sensors agree, but they are agreeing on a physical lie. A really tragic textbook example of this is the Pitot static system, which is what measures airspeed and altitude. In the case of Air France Flight 447, ice crystals blocked the Pitot tubes. Now, the sensors didn't break. They accurately measured the pressure inside the blocked tubes. But because they were all blocked simultaneously by the same environmental factor, they fed synchronized, perfectly voted but completely false speed data to the flight computers. Our source documentation on Flight 447 puts it pretty chillingly. These highly sophisticated aircraft can become a peril whenever computers go blind or if they are not receiving proper signals to elaborate. Relying solely on an automated digital picture is incredibly dangerous when the environment creates an invisible electronic fog. The system thinks it sees perfectly clearly, but it is completely blind to reality. Section 4. Deterministic logic versus common sense. So you gotta ask, if the data is just so obviously bad to a human being, why doesn't the system's digital brain just reject it? Well, we have to strictly depersonify the software layer here. Automated flight and navigation systems are generally deterministic. They calculate, but they absolutely do not think. They follow strict if this, then that programming. They completely lack the common sense layer of a truly intelligent, context-aware system. If the this is wrong, the that will always be wrong, regardless of how advanced the math is. Let's walk through this exact tragic progression using the 737 MAX MCAS failure as our model. It's basically a three-step cascade. Step 1. An environmental factor, like a bird strike, physically alters the sensor state. Step 2. The sensor continuously feeds that valid erroneous angle of attack data into the computer. Step 3. The deterministic system blindly executes its programmed rule. It sees a high angle of attack and commands a pitch down to avoid a stall. The computer flawlessly executed its code, but because the initial input was a physical lie, the cascade was absolutely fatal. This actually ties in perfectly with Michael Rasmussian's governance, risk, and compliance theory. He has this great line: a fluent answer is not the same as a defensible decision. An AI or an automated system can perform its math flawlessly. It can give a very confident, very fluent output. But if that output lacks a connection to physical truth, if it hasn't actually validated the evidence, the resulting decision is disastrous. Controls fail in behavior, not on paper. Section 5. The pilot in the loop. All right, so how do we actually fix this massive vulnerability? We have to bring it back to our physical engineering roots. What is the ultimate fail-safe when the math detaches from reality? Well, the industry is shifting from the dream of full automation to the reality of augmented intelligence. My background is in construction management, and I can tell you, we learned early on that you can't just blindly trust a blueprint if the foundation right in front of you is visibly sinking. It's the exact same in aerospace or maritime navigation. In engineering, we don't keep humans in the loop because humans are perfect. Far from it. We keep them in the loop because humans are the only sensors capable of looking at the holistic context and identifying when the math doesn't match physical reality. The computer handles the heavy calculations, but the human must remain the final judge of truth. There is a catch, though. As the core scholar research points out, keeping humans in the loop absolutely only works if the human actually understands what the automation is trying to do. Automation's surprise happens when a pilot expects the system to do one thing, but it does something completely different. If the human's mental model is wrong, or if the interface is hiding what the computer is actually executing, that human failsafe breaks down. We end up fighting the machine instead of guiding it. But listen, when it's properly integrated, the human failsafe is just incredible. Look at modern maritime navigation. When a ship's bridge team is dealing with something crazy like GPS spoofing, and their electronic screens show targets that just do not make sense, they have to revert to direct physical observation. They literally look out the window into the physical world, through the fog or the dark, to confirm if a digital target actually exists out there. They are prioritizing contextual reality over calculated data. And really, this is the ultimate lesson I want you to take away from this explainer today as the InfoEngineer. Truth comes before intelligence. A system can be incredibly smart, it can have quadruple redundancy, and it can run the absolute most elegant fusion algorithms in the world. But if it isn't anchored in ground truth, if it lacks the physical context of the real world it operates in, it is completely vulnerable. Which leaves us with a pretty provocative thought to chew on. As we rush headfirst into this era of fully autonomous systems, from self-driving cars navigating our busy streets to next-generation flight networks in our skies, who or what will be the final judge of truth when the sensors all agree on a lie? Thanks for joining me on this explainer. Until next time, keep questioning the systems around you.